I will. Thank you very much. Before I share my screen, let me first thank you for inviting me to give this seminar. Ευχαριστώ, I speak 5 words of Greek. That was 2 of them. It's been a while since I gave a seminar, and I think we all have to get going again once the pandemic slows down a bit. So I appreciate the opportunity you've given me to force me to think about all the recent results we've published with LEGA-C. There's 30 papers by now, and there's no way I can do them all justice. And there's also no point in an audience that is as varied as this audience. So I'm first going to provide some general picture of how we see galaxy evolution these days, and then describe how the work of my group and myself have contributed to that over the past few years. So I'll first set the stage in general, and I'll start sharing my screen now. Supposedly this is now a full screen slide presentation.
Correct, yes.
Okay.
You see the full screen. So
the outline is it's very simple. I'll start with an introduction about galaxy formation in general and some of the insights we've learned from imaging, ground-based imaging, Hubble imaging, Spitzer, etc. And then in the second part of the talk, I'll zoom in on the spectroscopy side, where LEGA-C is playing a prominent role these days, because it's the first time we see the stellar populations and internal stellar kinematics of galaxies beyond the local universe. But first, let's take a look at the general picture of galaxy formation. Of course, it starts with the concordance cosmology, where first WMAP showed what the structure actually is in the microwave background. And to put it in very simple terms, you can take these fluctuations, these temperature and density fluctuations you literally see in the cosmic microwave background, and predict how the large-scale structure of the universe will evolve. And that's shown here on the, can you actually see my cursor?
Yes, we can. Yeah.
Okay.
It's a little bit small. I don't know if you can make it a little bit bigger if you have the option, but we can see it.
Okay, we'll have to do with this. So if you take these initial conditions and you run a numerical simulation about how the matter will continue, how the structure will continue growing, you predict something like this. There's the Millennium simulation in 3 different boxes. And what you see is this very typical large-scale structure. And one of the great results of observational cosmology is how well this agrees in a statistical sense with the observed galaxy distribution. Here's the old CFA survey, the Sloan 2DF. They revealed that galaxies, every little dot here is a galaxy, every little dot here is a dark matter halo. The clustering properties of the galaxies and the dark matter is basically identical. So what we have then is a universe that is dominated by the dark components, as we all know, and a very small fraction of ordinary matter. But that very small fraction, of course, makes up the galaxies. Now, I want to stress how important it is to have this concordance cosmology for people like me who are interested in the galaxies, because when I first started reading galaxy evolution papers as a student, we didn't have a concordance cosmology yet. So you measure a flux and an angular size in the sky, but you don't know what it means in terms of luminosity and physical size. So over every result you wanted to infer about galaxy evolution, you had to make various versions for an open universe, a flat universe, etc. Different Hubble constants even. The fact that we have concordance cosmology meant that galaxy evolution could take an enormous leap forward, because you didn't have to worry about interpretation of your fluxes anymore. So that brings all the questions into focus, and you can formulate the question of galaxy formation as, how do gas and stars assemble in the centers of dark matter halos? So what we think these days, and now basically becomes a summary of my talk before I've given it, but it's also a much broader summary of the field as a whole, is that you start with a dark matter halo that is cooling rapidly. So this is the dark matter halo. It's cooling rapidly feeding a proto-galaxy or young galaxy at the center with an irregular morphology. There's star formation going on. The potential is not very deep, so it's very effective in producing these outflows in all directions. And that's an early stage of galaxy formation. Right? It doesn't really matter at what redshift this happens. That depends on the final mass of the halo, of course. But there's very fast growth. I draw thick arrows when there's it's a very prominent process. This galaxy changes shape all the time because its growth rate is as fast as it doubles in mass very quickly, quicker than the dynamical timescale. So this leads to irregular morphology and constantly changing morphology. At some point, this transitions to a phase where the halo got bigger. There's still significant cooling going on, but the galaxy itself has settled into a disk that doesn't change angular momentum direction all the time. It's a regularly rotating disk. Much of the outflows now cycle back onto the galaxy, so angular momentum is distributed, redistributed. The chemical elements are redistributed. There are outflows driven by the star formation that are now mostly bipolar, so perpendicular to the disk. And this is what I think of as the main stage of galaxy formation. A black hole starts forming in the center, but it doesn't do much yet. It's hard for gas to reach the black hole because of the still very efficient star formation driven feedback. Okay, then something important happens. At some point, the star formation is not, the feedback from the star formation is not sufficiently effective anymore to prevent gas from reaching the center. So now the black hole starts growing quickly and putting in a lot of energy into the halo. And at some point, that cumulative energy that the black hole has entered into the halo approximately equals the binding energy of the halo. At some point, that threshold will be crossed. This is a picture presented in a recent paper by Sandy Faber, and a student of hers that I was privileged to be a part of. So the idea there is that at that point, the halo can't cool anymore, right? Together with the shock heating that happens to the new material that falls onto the halo reaches this virialized state, and there's no cold flows anymore. But the galaxy itself is still full of gas, right? This black hole feedback might have heated up the halo, but it didn't blow out all the entire ISM. So this galaxy will keep growing in stars until it runs out of gas. But that gas is not replenished from the halo because the cooling stopped. So then after a gigayear or so, the gas supply has run out, and you have still a disk, but it's become quiescent in terms of star formation. So then the late stage of galaxy formation, at least for massive galaxies, is that the only way to grow anymore is by merging with smaller satellite galaxies. So slowly the disk-like structure of this quiescent galaxy gets destroyed, the stellar orbits get scrambled, the galaxy grows in size, the black hole grows in mass, so every little galaxy brings in its own black hole, and eventually the disk is destroyed. Now, over the timescale of gigayears, this hot halo will still slowly cool. And there, the idea, it's been around for many years, of course, is that occasionally the radio mode AGN switches on to keep the halo hot. So it's the maintenance mode feedback picture. So I've, in a few minutes now, summarized the entirety of galaxy evolution. I've cut many corners, I've ignored many aspects, but this is the basic picture we have these days. So in the end, it's a very simple sequence where you start with an irregular galaxy, a main formation stage, a quenching process, and an early type galaxy. Of course, how far a galaxy gets along this line depends on the mass of the halo. So basically, the rest of this talk is about explaining why we think any of what I just said is true, the main aspects of it. And I'd like to start with, I've talked about disks, I've talked about star-forming galaxies and quiescent galaxies. And now I want to show where that knowledge comes from. what kinds of observations, and I'd like to start with imaging in the most general sense. So people for years have done these surveys, of course, in the infrared and the UV, and we think we know the cosmic star formation history. Now, I've plotted that here in a way that you're not used to, but it's based on the Mandel-Dickinson review from a few years ago. But here I show as a function of the age of the universe, the fraction of the stars that will ever form, taking the functional form that Mandel and Dickinson provided. So it's a cumulative star formation history. And so it starts at 0, obviously, and then you see how at redshift 3, 2, 1, and 0, the mass in stars accumulates. This extrapolation is based on the extrapolation of the current downward trend in star formation density in the universe. So you see several things here that you might not think about very often, but one is that the universe is basically done forming stars, right? Galaxies are basically done forming by today, which is why we look back at high redshift when galaxies were in the middle of their formation epoch, even redshift 1, right? That we don't think of high redshift anymore. As far as galaxy surveys is concerned, it's a very different epoch than redshift 0. So anything that's happening in the future is a rounding. It's a rounding error on galaxy formation. It's basically done. Okay. Now, not only do we know how many stars there are in the universe at different epochs, we also know how they're distributed over galaxies with different masses. So here's the stellar mass function, the number density on the y-axis, the stellar mass on the x-axis. So here we see the mass function. It has this exponential cutoff here near what we call L star, and the distribution is described by a Schechter function, or maybe a double Schechter function. This red dot is where the Milky Way sits, more or less, so near the knee. Okay, how does this thing evolve? This is at relatively low redshift. At higher redshift, you see gradual change. What you see is a downward shift. Right, so at all masses, the number of galaxies increases over time. And as a consequence, we can say that most stars reside at the same mass at all cosmic times, between redshift 0 and 3. Right, and if you multiply this mass function by the mass, you get the peak around L star. So most stars live in L star galaxies, and L star doesn't really move with cosmic time. So at all cosmic times, most stars reside in galaxies with Milky Way mass, or a bit more. It doesn't really change. Now we then go back to the dark matter halos. Dark matter halos evolve very differently. From redshift 2 to 0, you see a horizontal change in the mass function, where the galaxies go up and down, the dark matter halos go left and right. That's why it's so challenging for the simulations to reproduce the mass function. You really need to push around these baryons and the dark matter halos very aggressively in order to make the mass function work. And that's basically one of the big challenges in the field. But to make sense of the stellar mass function and in the context of the halo mass function, people have worked on the galaxy halo connection. And this is it's an older plot by now from 2010 by a paper by Benjamin Master, but others have worked on this as well. They built an empirical model about how the stellar to halo mass ratio varies with halo mass. So the Milky Way lives in a 10 to the 12 solar mass halo. So it lives about here. It adds up. If you do this multiplication, you get the stellar mass of the Milky Way. So there seems to be a peak in the efficiency with which a halo can convert its baryons into stars. So at that peak, about 3% of the halo mass is in stars, or 20% of its baryons. At lower and higher masses, those fractions are lower, and here that's attributed to the star formation feedback that slows down the star formation process. And here the feedback is supposed to come from the black hole, right? That's the standard story. So I can now generalize the point even further that I made before, that most stars reside in Milky Way dark matter mass halos, 10 to the 12 solar mass dark matter halos at all redshifts up to redshift 3. Because if this relationship between stellar and halo mass, it evolves somewhat by a factor of several, but not order of magnitude. So then if, go back to this slide, at all redshifts up to 3, most stars live in galaxies of this mass, and the same is true for the halos. Sorry. Awkward break. And so at all redshifts, most stars reside in 10 to the 12 solar mass halos. It's a key result of this work. And if I now draw my schematic view of galaxy formation onto this diagram, you have the low mass irregular galaxies here with a lot of feedback pushing down this conversion from baryons to stars to a low percentage. And the main formation phase here, then you reach the peak. And then the black hole kicks in and stops the star formation. But the halo keeps growing, so the stellar to halo mass ratio goes down. Now, there's a lot of arguments about how steep down this is because of intracluster light and mass measurements, etc. But the key is at least it flattens. It doesn't keep going up. It flattens or goes even down. I don't want to have that discuss that further now. Okay, so I've drawn these galaxy shapes, right? I've said, okay, galaxies, they grow in size, they change from disky to elliptical, but why do we know that? Well, one of the main reasons we know what galaxies look like is, of course, the Hubble Space Telescope. So now I'm gonna, for a little bit, talk about what's now basically old news. The Candle survey is a decade old, but we've learned a lot there. So for the first time, we had a very large sample of galaxies, hundreds of thousands actually, where we resolved the spatial structure in the rest frame optical. So not in the UV where you're dominated by star formation and dust, no, the rest frame optical where things are a little better. So here are just 15 images of star forming galaxies at that knee of the mass function, where representing the dominant mass fraction at redshift 2. Now these are star forming galaxies. It's a combination of rest frame UV and rest frame optical images. So there are some exceptions here, here, notably, and here, but most of these galaxies are disks, right? So combined with the previous results I mentioned, this means that not only do most stars live in these L-star galaxies, they're disk galaxies, just like the Milky Way. They have different properties, but they're disks. These galaxies also account for most of the star formation in the universe. I didn't really show that, but I have to take my word for that right now. So now we have a very broad conclusion that most stars live and new stars form in Milky Way mass disks at all redshifts, up to at least redshift 2. And that's most of cosmic history and most of the star formation of the universe. Okay, so these are star forming galaxies. How did I select them as star forming? Well, as a quick interlude here, we usually do that in this, or we often do this in this color diagram, rest frame U minus V color versus rest frame V minus J. And galaxies populate this part of parameter space there. And we draw a line separating quiescent galaxies here. So non-star forming. As AGN people, you might think of quiescent as non-AGN, but when I say quiescent, I mean non-star forming. Apologies if that is a little confusing. And then star forming down here. So if you have a young blue star forming galaxy, it will be over here. If you put dust in there, or you put a disk edge on, it moves in this direction because that's the direction of attenuation. To get over here, you have to have an old stellar population. You have to have a strong Balmer D4000 break. Whether that's entirely clear or not doesn't matter, but we use this two-color diagram to separate the quiescent galaxies from the star-forming galaxies. That's the relevant thing for now. So if I draw my schematic galaxies in there, you can also think of that sequence again, where you have these irregular galaxies here. They're low mass, low metallicity, dust poor, so they'll be blue all the way. Then you have more massive disks, more metals, more dust, and you move along that dust sequence. If you stop forming stars after a while, you move to the red colors in that direction. Okay. So here again are these images of the redshift 2 star-forming galaxies that I've said, okay, they're mostly disks. We also see that in the Census index. So these things have exponential light profiles, just like present-day disks, and they're quite large in extent. At least large in contrast with the quiescent galaxies at the same redshift. You see how different these things are in structure, right? You see that these are generally large, these are generally compact, with very high central surface brightnesses, very high central mass densities. If you go back and forth, that's the most striking difference between the two populations. Dense, high mass density in the center, low mass density in the center. You can already relate that to black holes, right? These things are going to have higher black hole masses than these things. They have more mass in the center. That probably also is true for the black hole. Okay, let's quantify this a bit. So now I put the size of the galaxy, the half-light radius, the radius that contains half of the total light, against the stellar mass. In red is the quiescent galaxies, in blue the star-forming galaxies. This is from candles, so there's not too many low redshift galaxies. And I make a fit for the size-mass relation for the star-forming galaxies and the quiescent galaxies separately. If you then go to higher redshift, you see the same trends. Now I have more galaxies, it's a dense beam survey, so I have many more galaxies at high redshift. And again, a fit to the populations, and the dashed lines are the same as these for reference. So if we then keep going to higher redshift, you see how things change in some ways and things don't change in other ways. What we see is that all galaxies are smaller at high redshift, most notably the quiescent galaxies. But that happens in a very systematic way, because the slope of these size-mass relations don't change. Also, the scattering in the size-mass relation doesn't change a lot. So there's a lot of regularity here, hidden in this very dramatic structural evolution. It's a very good constraint for the galaxy formation models, of course, because they have to reproduce this regularity. So at all redshift, we see that these quiescent galaxies are more compact than the star-forming galaxies, except at the high mass end, things come together again. So now the question is, what now? Before I continue, we can draw our schematic galaxies again. So this is just an example how you can think about this. Yeah, the low mass star-forming galaxy with an irregular morphology at redshift 3, it settles into a disk. This is now an individual galaxy that we're tracing through cosmic time. It settles into a disk, it grows up nice and easy. Black hole mass reaches a certain mass here and it starts heating up that halo so that the galaxy stops forming stars, but it's still a disk. And then nothing happens anymore except that over the intervening 10 gigayears or 8 gigayears, this galaxy will merge with its neighbors, slowly destroying that disk and becoming a large elliptical. So all the mass growth from here to here is due to merging, and all the mass growth here is through star formation, by and large, right? There's always a mix, but schematically, that's how you can think of it. Again, I've talked about disks and I've talked about star formation histories in a way, but that's basically an educated guess, right? With these images, you can't really know that until you do spectroscopy. So bigger HST surveys are not going to give a better answer because we're clearly not dominated by number statistics in these plots, right? So we need a different kind of data. So now we move on to basically the main part of the talk, but it's all integrated. So I'm not going over time in terms of introduction here. What can we learn from spectroscopy and specifically from the LEGA-C survey, which targets the stellar populations and stellar kinematics at redshift 1. Of course, people have done a lot of spectroscopy before, but it was usually the emission lines, orbital gas, or just to measure a redshift. It's really the first time we see the stars in the spectra beyond the local universe. Okay, the questions that drive the survey are all related to that big schematic picture of galaxy formation. How do galaxies assemble? When do they form their stars? What's their star formation history? And why do they stop forming stars? And what happens after? So the basic tools we have is we have access to the stellar population, so the star formation histories, chemical enrichment, and the stellar dynamics. So the total mass of the galaxy. We can compare it with the stellar mass, the dynamical structure. Is it a rotating disk? Is it a more elliptical-like galaxy where the orbital structure is more chaotic? We can connect that with what we already know from the Hubble imaging and with ongoing star formation. So that's the tools we have. So what is the survey? Very briefly. Key is that it's a K-band selected sample of all morphological types. So it's a good mix of star forming and quiescent galaxies. That's new. In this redshift range up to redshift 1. We spent more than 100 nights at the VLT collecting these data. And that's because we did 20-hour-long integrations of individual masks of objects. So there were about 24 masks with VMOS with 100-something galaxies each. And each mask was integrated for 20 hours. So then we get high singleton noise, at least for high redshift, with high resolution. So we can do the stellar kinematics. And we just finished in this summer the third and final data release. So in that sense, the survey is finished, but we're smack in the middle of producing the scientific results. So one more plot on the sample. Here's this stellar mass as a function of redshift, and here's the knee of the mass function, stellar mass function. So here you see that LEGA-C really targets the high mass end of the mass function, but not only the very high mass end where the ellipticals live, but we go well below, especially at the lower redshift end. So we basically sampled the galaxy population around the knee of the stellar mass function, where most of the stars live and where most of the new stars are born. The color coding is the completeness. That's not so important now. It's very important for completeness corrections, etc. But I don't want to focus on that. So what do the spectra look like? This is basically plotting 3,000 spectra at the same time here, where I've color coded each one according to its global stellar age. So as given by the H gamma absorption line index. Okay, let's take a step back. What we see here is lots of absorption lines, right? We see the Balmer lines, H beta, H gamma, H delta, higher order. And we see lots of metal absorption features, CM, calcium, iron, etc. Dozens of metal absorption features in each individual galaxy spectrum. I've taken this H-sensitive H gamma line here and sorted them by that H gamma absorption strength. The ones with the strongest absorption have the bluest color, and the one with the weakest absorption, so the oldest galaxies, have the red color coding. So now you see how the galaxy spectrum systematically changes as a function of stellar population age. There are emission lines in these spectra. For the purpose of this plot, they're being removed. So let's look in a bit more detail at some individual galaxy spectra. So here is a post-starburst galaxy. I'm going to talk about post-starburst galaxies a bit more later. Here's a Hubble Space Telescope image. By the way, this all takes place in the Cosmos field. Those working on the AGN might be familiar with that field and the data sets available there. So we take advantage of the multi-wavelength photometric data set as well. So here's a post-starburst galaxy. It's characterized by this very strong Balmer line absorption features. In red, you see the stellar population model that we use to measure the stellar velocity dispersion. So we Doppler broaden the model until it matches the spectrum. Another example here is an old elliptical. So now we see a spectrum very rich in structure. The black line is the data, and now there's two models. Doesn't matter too much. One is based on theoretical templates, the red line, which shows some shortcomings here and there. And then in green, the model based on empirical stellar spectra, stellar templates from the Vazdeikis SPS model. This is just to show that all these wiggles in the spectrum are real information, not noise. Right? That's the key point I want to make here. So for star-forming galaxies, the spectra are a bit noisier because their surface brightness is lower, so it's hard to obtain the same singleton noise. But here you see very nicely that with our spectral resolution, we can resolve the stellar absorption for the Balmer lines and the ionized gas emission. So we decompose the spectrum into two components there, and we get a stellar velocity dispersion and a gas velocity dispersion. So we can study the kinematics of the gas and the stars separately. Okay, to put LEGA-C in context compared to what's come before, in the previous 2-3 decades, people have slowly taken spectra of massive ellipticals at redshift in the same redshift range, 0.6 to 1, and it all amounts to about 180 massive ellipticals with stellar velocity dispersions and a subset of just 60 galaxies with these Balmer line star population measurements in general. So what LEGA-C now produces is a 50-fold increase in sample size in terms of galaxies with stellar kinematic information and stellar population information. So before we had massive ellipticals here with velocity dispersions of 200-300 kilometers per second, a few things here. Now we have thousands of galaxies all over this parameter space. Right? We have everything in here. So what can we do with that? What do we learn? So let's first take a look at the stellar populations. I've shown these spectra before. And first I'm going to summarize this spectra in two numbers. I'm going to take the strength of this H delta feature. So here it's a weak H delta feature because it's an old galaxy. I'm going to compare that with the D4000, the strength of the D4000 break. D4000 break is the ratio of the flux here and here. So old galaxies have a strong break, young galaxies have a weak break. So if I make this measurement for all the galaxies in the survey, I get something like this. So here's this H delta feature versus the D4000. Guinevere Kaufman made this plot very famous 20 years ago based on Sloan. So for Sloan, you see the distribution of the galaxy population is a mass-matched sample. So most galaxies are down here. So strong breaks, weak H delta, they're old. In LEGA-C, you see two peaks. There's an old peak and a young peak. And the old peak has shifted compared to the Sloan because even old galaxies are younger in redshift 1 than in redshift 0. And there's a much more prominent peak of young galaxies. So this is schematically, again, what I'm showing here. There's the old galaxies here, dominated by ellipticals and quiescent galaxies. And the galaxies in their main formation phase live up here. So then we see that for LEGA-C at redshift 1, 50% of these massive galaxies, right, there's equally strong peak here and here. 50% of the massive galaxies are in the middle of the main formation phase. For Sloan, it's very different. We're basically all old. So the present day universe is too old to witness galaxy formation. It's a different way of saying what I said before. Okay, recently we published a paper comparing this distribution of H delta and D4000 with the TNG cosmological simulation. So again, we see LEGA-C in blue here with the two peaks. Here in histograms and the two separate parameters, and we compare that with the prediction from the TNG simulation. I have no time to explain how these mock data were generated, but that's what they are, mock data based on the TNG cosmological simulation from Pilipich and Nelson. So TNG mostly lies near where LEGA-C is, right? And there's a very similar distribution in width and by modality, even in H delta. So that's a big success for the simulation because it didn't in any way try to reproduce this observation, right? Here, the model was actually predictive because these observations didn't even exist yet when the simulation was made. In detail, there's differences. You see this offset here. You also see that the LEGA-C is more bimodal than TNG. Something's not quite right with the simulation, but that's where you learn. There's different interpretations for this offset. It could be the stellar population models themselves. It could be the star formation histories of the galaxies in TNG compared to reality. We don't know for sure. If you're interested, please check out this paper that we published a few months ago. Okay, so decent agreement with the TNG simulation, but important differences in detail. Now, of course, summarizing the spectrum in two numbers is almost criminal, right? We have high singleton noise information in a broad wavelength range. So why throw away most information? Now, what you want to do is you want to model the entire spectrum. Now, the first thing we did, this is a few years ago now, is assume that all stellar populations in these galaxies have a solar metallicity. It's a huge shortcut, but we just wanted to see what happens. We're currently working with Angelos actually to make this much better and do a full modeling of the stellar metallicity, the stellar population age. It's much more complicated. But we just wanted to see what happens if you assume that all stars in these galaxies have solar metallicity and solar abundance ratios. Can't be too far off, right? It's impossible to make a very low mass, very low metallicity massive galaxy. Just impossible. So what we do, we have, I don't know if you can see this, we have 12 H pins. And the red line is a linear combination of the stellar templates that represent these 12 H pins, right? The galaxy is a superposition of star populations with different ages, and that's what we do here. So the model fit looks really good, and what this model implies is that most stars in this galaxy are young, right? This is the age of the universe, this is the time of observation, and very little star formation in the early universe. So we do that for many galaxies. So here's 3 examples of young galaxies with most star formation recent, before time of observation. And here are 3 old galaxies where most of the stars formed early in the universe. This one had a little blip later on. We wrote a paper about that specifically. I don't have time to go into that. So every galaxy is decomposed into a star formation history here. And if you take all these star formation histories together and group them in bins of mass, or in this case, velocity dispersion, you get the star formation history for the entire galaxy population split by mass. So we see for high mass galaxies that most stars formed early, and for low mass galaxies, it's the other way around. Another way of showing that the star forming galaxies at redshift 1 and slightly below are in the middle of their main formation phase. They're not done yet, right? It's Milky Way mass galaxies here. If you look at the Milky Way today, the star formation rate's been declining. The thing is basically finished. So to put this into context of the schematic galaxy formation model I presented early on, these massive galaxies, they're very far along. Right? Their main formation phase was in the first few gigayears of the universe, and this quenching event happened several gigayears prior to observation, and now we're sort of in this phase where the galaxy is in the process of growing through dissipation, is merging, and there's no more star formation. That isn't in the future, right? Where these things become massive ellipticals. These galaxies are different. They lag behind in evolutionary state, so to say. In the early universe, they might not exist at all yet, or they're in this early chaotic formation stage. And only now they're in the main formation stage, and all the quenching and quiescence is still in the future, if it even reaches that state, right? If the halo stops growing, then the galaxy will stop growing too. Okay, so that's a very clean picture in a way of this is how galaxies form, but of course reality is much more complicated. And one complication is that the age distribution in the size mass plane is very complicated. So now I'm going to take a slight detour and talk about the post-star forming galaxies. What you see here is again the size distribution compared to the stellar mass distribution for quiescent galaxies. Star forming galaxies, that's the blue shaded region here. They're not shown. But now we have from LEGA-C the stellar population age information. So here the age delta absorption feature, right? So weak absorption means old. The dark point are old galaxies. Strong absorption is young. So those are the young galaxies. There's a bunch of scatter, but you do see that most old galaxies are here, and then there's young galaxies here and here. So if you do some smoothing and binning, then it's a bit more clear. You see old galaxies here and here, and young galaxies here and here. Now it makes sense that young galaxies are here because they're like the star forming galaxies. I'll get back to that in a second. First, I want to point out that this reconciles some tension in the literature that has existed for many years. Because there was one series of papers that said, if you go to the smallest scales, small galaxies are older than large galaxies. If you look at quiescent galaxies, and that's true. Right? These smallest galaxies are younger than average. At the same time, there were people, including the same groups of authors, seemingly contradicting themselves, but not really, that young galaxies are smaller than old galaxies. And that's true because these galaxies are younger than these galaxies. That reconciles these two seemingly contradictory statements, but they're actually true at the same time because there are young galaxies here and here. Now it makes sense that young quiescent galaxies live up here because they are just like the star-forming galaxies, right? They're disk galaxies, the halo quenched, star formation stops after gigayear, but nothing happened to the galaxies. So structurally, they're the same as the star-forming galaxies. They're disks, they're fairly large. So how about the young galaxies here? How do you make those? Now, these are the post-starburst galaxies that rapidly stopped their star formation in the recent past. And what can we learn from those with LEGA-C? Well, here's an example. It looks like a compact galaxy, right? They're small in size. And we have spatially resolved information. I haven't mentioned that yet. I made a mistake of not illustrating that before, but here's the LEGA-C slit that lies on top of the galaxy image. So normally I've only shown integrated spectra now, where we take all the light in the slit together to show the integrated spectrum of the galaxy. But we have pixels here, spatial resolution elements along the slit. So we have different spectra for the center and for the outskirts. It turns out that these post-starburst galaxies, the spectra look different in the center and the outskirts. In the center it looks like this, in the outskirts like this. It's noisier, but the key point is that this H delta feature is stronger here and here. It's a very subtle effect, but we showed this in this recent paper by Francesco De Eugenio. There is an H delta absorption gradient in the galaxy where the inside has for the post-starburst galaxies, this is now a combined result for not just this galaxy, but about 25 of them, where the H delta absorption is slightly stronger in the center than the outskirts, meaning that the center is younger than the outskirts, with the opposite of what normal galaxies look like. Here's a control sample of other quiescent galaxies that, if anything, show a positive gradient. To make sense of this gradient, you also have to look at iron absorption features. I don't have time to go into detail, but the conclusion we draw is that there are positive H gradients in post-starburst galaxies. So the center is younger than the outskirts. This deviates entirely from the schematic picture I've shown so far. The way we explain this is that this standard sequence, evolutionary sequence for a galaxy gets interrupted by a major gas-rich merger. It completely disrupts the evolutionary sequence and radically changes in a short amount of time the structure and the star formation history of the galaxy. And the reason that these galaxies stopped forming stars is probably because the starburst itself, in combination with the AGN, drove out all the entire ISM, which doesn't happen normally. Right? So this is not a matter of the halo becoming hot and stops cooling and then the disk slowly starves. No, here you actively remove the ISM from the galaxy and you expose this young center that recently formed because of this gas-rich merger where all the gas flowed through the center. That's very briefly what we think happened here. And that's why we say we have multiple pathways to quiescence. The standard one, without dramatic structural changes, and the more dramatic one, where you're doing this rapid quenching by a blowout phase driven by quasar or the starburst itself. I'm quite agnostic about that. Okay, I've talked about disks, I've talked about ellipticals, but to do that properly, we need to know, this is the last topic, we're running out of time, I think, the stellar kinematic component of LEGA-C. So as I mentioned before, the standard measurement is the integrated stellar velocity dispersion from the broadening of the absorption lines. And the first thing that comes to mind, at least my mind, is you put it on the fundamental plane. We have the fundamental plane, if you may recall, is the relationship between the effective radius of a galaxy, its surface brightness, or here the surface mass density, and the velocity dispersion. It's one of the tightest correlations in astronomy. And the way to think about this is that you basically compare the dynamical mass through the velocity dispersion with the stellar mass, the surface mass density. That's deep down what the fundamental plane is, a relation between the dynamical mass and the stellar mass. Interestingly, the star-forming galaxies here in blue lie on the same fundamental plane as quiescent galaxies. A different part, right? We know they're structurally different, but they lie on the same plane. So whatever you do to a galaxy, you can make these mergers and all kinds of crazy stuff. You have to stay on this plane. It's a very tight constraint on galaxy formation models. Now, I don't want to belabor this point because I have one more interesting thing to show, and that's the spatially resolved information we have on the stellar kinematics. So along the slit that we have for LEGA-C, we can measure the velocity and the velocity dispersion at each spatial element, producing the rotation curve and the velocity dispersion profile for both the emission lines here in blue and the stars in red. So it's really the first time we have this for galaxies at high redshift, right? Now what we do with this, of course, this is an HST image. Our spectrum is ground-based and its spatial resolution is 10 times worse. So this whole thing is heavily convolved. This is a heavily convolved picture of the stellar kinematics. So we have to build a model. No time to explain the model. It's all explained in a recent paper by Josje van Hout. Well, what we do is we combine the velocity dispersion and the velocity to produce the second order velocity moment. We built a dynamical model that tells us what the dynamical mass is and the orbital structure, the ratio between ordered motion in a disk and random motions through the velocity dispersion. So a high V over sigma means a disk, a low V over sigma means an elliptical, by and large. Okay, we managed to build these models for about 800 galaxies. So we can build this diagram and show how V over sigma, the degree of rotational support, changes with the shape, projected shape of the galaxy. You're familiar with Atlas 3D and SAMI and all these integral field surveys from the local universe. They produce diagrams like this. Now we can do the same for high redshift for the first time. Now this is a projected V over sigma. So for disks, edge-on disks are here. They're flat in projection and they rotate. Yeah? Phase on galaxy, phase on disks, you don't see the rotation. So V over sigma is low. Because we have dynamical models, we can deproject that. And you get this. It is the same data points, but now I have from the model the deprojected V over sigmas. Okay. The color coding is a Census index, so that's a structural parameter where 1 is an exponential disk that we associate, exponential profile that we associate with disks, and index 4 is the Vauquelin profile that we associate with ellipticals. One thing to note here, that's fairly well mixed, right? It's not very clear, the separation between disks and spheroids. And that's because of this schematic image picture of galaxy evolution. Once galaxies stop forming stars, they don't stop being disks. They don't stop rotating, right? They still have a high V over sigma. Only over time do they reduce their V over sigma through this dissipation, this merging. That's the picture we see appearing here. Okay, I'm running out of time, so I need to wrap up. But this is a gold mine for further investigation and compare the dynamics of high and low redshift galaxies on equal footing. First time that's possible. So final piece of context here. So after quenching, these disks stay here, right? They keep rotating. And only over time, they slowly become rounder and they lose their rotation. And that explains the large scatter in V over sigmas and shape for the quiescent galaxies. Okay, the only thing that remains is the conclusions, but I've presented enough conclusions throughout the talk. So I'll leave this up and take questions. I'll leave it up for a minute and I'll switch off the screen sharing so we can have an actual conversation when answering questions.
Okay, thank you very much, Arjen. Are there any questions? Okay, maybe I can use my privilege as organizer to ask the first question. So I was quite surprised. Well, there was this plot that you showed, the star formation rate or specific star formation rate as a function of time. It's this, your star formation history plot, where you saw that for the passive galaxies, you know, most of the star formation was happening at early times, and it was the exact opposite for star forming galaxies. What I found a bit surprising is, first of all, that at early times, star forming and passive galaxies only have a factor of 2 difference in star formation, specific star formation rate. And I'm not, maybe that's because of the stellar mass and not so much of the star formation rate. And also the second one is that unlike the star-forming galaxies, the passive galaxies do not appear to show peaky star formation histories in the past. And I'm just wondering if that's an analysis limitation. You cannot constrain bursts of star formation when they happened ages ago.
Yep, I think you're right on both accounts. This contrast is not very large, but that's because this M star here is the stellar mass at time of observation. Right, so these are more massive galaxies than these. So these are relative star formation histories. Right, the integral under these curves is unity. Right, so plot absolute star formation rates, these are going to be a lot higher than these.
Than this over there.
Yes, that's the first part. The other part is, you basically see it here, right? In these star formation histories, the oldest age bin is very wide because it's hard to see differences between stars that are 3 and 5 gigayears old at a singular noise of 20. So what happens in terms of star formation history in the first 4 gigayears of the universe is still very hard to tell.
Okay.
So yeah, this all gets averaged out over this period of 4 gigayears. So it looks like a smooth star formation history when you average all the galaxies together, but it's not necessarily the case. In fact, I think these are not reasonable values, right? 30, 20 solar masses per year for massive ellipticals are redshift 4. Now in the main formation phase of these massive ellipticals are going to be 1,000 solar masses per year.